What I'd like to talk about is lessons learned from building a WebRTC application at internet scale. And to some degree, this title is a little bit of a misnomer because what I'm really going to be talking about is sort of lessons learned from powering a WebRTC application at internet scale. And talk to you all a little bit about some of the learnings we've had through the process, both on a client side, but also from a services and sort of cloud infrastructure side in terms of all of the dimensions which go into play to make that happen. And just as a quick introduction, before I delve into all of the details, my name is Badri Rajasekar. I work for a company called TokBox. And TokBox has a product called OpenTalk. And OpenTalk is a sort of a cloud-based service. It's a hosted cloud infrastructure which provides a whole bunch of APIs and SDKs for applications to sort of embed real-time audio, video, sort of communication experiences into your application. Whether it's a mobile application or whether it's a web application, you can get stuff embedded in there. And to some degree, as a platform provider, as somebody, and we have all these apps built on top of us, we have a rather unique vantage point in terms of seeing all of the behavior of real-time applications at scale, right? We see the behavior across a whole spectrum of topologies, a whole spectrum of deployments. And so we've had some interesting observations from that vantage point. And before I quickly sort of jump into all of the details, I wanted a quick show of hands in terms of how many of you know a whole lot about WebRTC? Okay, so I think it might be useful to sort of very quickly talk about WebRTC and give you guys a little primer. WebRTC is really revolutionizing real-time communication, right? And if you've not heard about it, it's basically a series of protocols and standards which enable sort of plug-and-free browser-to-browser real-time communication, right? And back in the day, there was Flash, and then you could use all these protocols like RTMP or RTMFP. And I think WebRTC is sort of a very concerted effort by a whole bunch of browser vendors to build all of the rich functionality to enable sort of browser-based real-time communication, right? And at the top level, these browsers actually support a WebRTC API, which is essentially a JavaScript API, very easy to sort of invoke, and then you can actually use this API to sort of negotiate and sort of start real-time communication across from browser to browser. And there's a whole bunch of support as well, which sort of comes into play. There's a bunch of support for media capture in terms of being able to access all these hardware devices. There's the technology which enables the negotiation of calls itself, mostly using SDP. So for all of you guys who are sort of from VoIP world, you'll probably be very familiar with the offer-answer model and sort of SDPs for negotiating connections. A whole series of things. ICE is mainly used for connectivity checking. And DTLS is essentially used for sort of key exchanges. And stun and turn are standard sort of protocols for NAT traversal. Let's say you were behind a NAT and you had to sort of relay it through a turn server, or you'd use a stun server to get your public IP, so on and so forth. The actual media is secure RTP and supports a variety of codecs. And the entire codec situation is a little bit of a mess, but I could talk about that for 4 hours, so I'm not going to go there. And just in this talk, what I'd like to do is, talk to you guys a little bit about some of the learnings we have had through this process. We've made a lot of mistakes in the process. We don't have all of the right answers. And some of the lessons I'm going to be sharing with you all might be controversial. Some of them might be obvious. Some of them might be counterintuitive. But I just wanted to sort of talk to you guys about our journey through the process. So, jumping into lesson number 1. In real-time communication applications, there's a bit of a tension between identity versus ease of use, personalization versus anonymity, right? There's a lot of talk about identity and anonymity and all this talk about privacy, and all of those are pretty important, but one of the areas outside of authorization or service or personalization, which might not be very intuitive, is the call model, and especially when you're working in a real-time communication application, the call model has a pretty big impact on identity. And by that I mean, let's say you were on a one-to-one call where I pick up the telephone, I dial a phone number, and I can reach somebody. That's sort of the direct calling model, which is used in a lot of one-to-one calls, right? If A wants to call B, A needs to know B is first reachable, some sort of presence, offline or online. And then I should be able to send an invite to B, and B accepts the call. And the ability to reach that endpoint, the ability to invite somebody implies a sort of presence or some sort of identity. So identities are very closely tied to the call model and the call topology, if you will, in sort of RTC apps. And the converse of that, when you expand your topologies beyond one-to-one calls, you get into this concept of a room-based model. Let's say 5 people were sort of meeting together. You send out a link, or you create a room, and everybody joins the room. And a similar sort of topology exists in telephony world, right? Everybody dials into a conference bridge, puts in some PIN number, where you don't really need identity of the people joining in. All you need is the concept of a room and some sort of scheduling around rooms. So I think one of the key lessons we learned having gone through all of this process is when you're thinking about real-time communication applications, it's really important to think about the topology and identities in the concept of topologies outside of all of the usual authorization, personalization, anonymity, and all of that which happen. And the second interesting factor to all of that is, and this may not be unique to RTC apps, but this is certainly something which we found out through the process, is identities and anonymity have an impact on adoption. And just to clarify what I mean is we had a concept of dog fooding a whole bunch of interesting RTC applications. So the black line is an application, a very polished conferencing WebEx type application which we wrote to dog food. And the one on the red is sort of this really hacky, off the cuff little conferencing application. One of our developers wrote in a hackathon, and they just put it up on a website, and it was running. And the only difference between these two apps outside of functionality was one, the app which is in black had this concept of strong identity for access, and the app in red had this concept of anonymous access where I could just send out a link. The link represents a room, and anybody can join that room, right? And we spent a whole bunch of time, and Lauren, who's our marketing manager, spent a lot of time even marketing this application on the left. But if you actually look at some sort of Darwinian process here, there was not a lot of uptake in that application, right? Whereas, you had a question?
Yes, I do. If your complicated case wasn't a new identity you were asking to create, but you were using our own with no authentication?
An existing identity. That's a good point. So it's not related to sort of identity fatigue, for instance, right? I'm creating yet another new identity. So the red application sort of blew the anonymous version basically blew the other app out of the water in terms of how virally it got adopted, right? And there seems to be this inertia, especially in real-time applications, where I want something quick and I can join, and there's sort of low barrier to use. So I think that the big lesson is call models sort of influence identity, and identity in turn might have a whole bunch of unintended consequence in terms of adoption and sort of ease of use. Moving on to the next lesson, I've always believed there are two big forces which drive the destiny of developers: scale and product managers, because both of them are completely unpredictable, and they change all of your fundamental assumptions all the time. And so one of the things is sort of important to keep in mind, and although it's sort of obvious, is to actually evolve incrementally until you no longer can. And while superficially this may seem obvious, again, in real-time communication applications, the topologies have a big impact on all of your bottlenecks, all of the sort of unintended sort of technical hurdles you might sort of encounter. And so I think it's really important to sort of very incrementally evolve, especially at scale. Things become completely sort of counterintuitive, right? And for all of you guys who work with applications at scale, things become counterintuitive, right? And it's really important to sort of plan for the unknown unknowns. I don't want to sound like Donald Rumsfeld, but I think it's a fair point. And as a very simple example, we were building a pretty large sort of internet scale application. We were rather powering a large internet scale application. And we had spent an inordinate amount of time, making sure we had the right infrastructure, we had the right capacity planning models, making sure we can scale a whole bunch of things. And the thing which actually got us in the end, which in hindsight was like, duh, we should have thought about it, was we had a very simple API called onSessionConnected, where when I connect to a session, I get notified that you are connected. And it sends an array of participants who are already in the call. And if you actually think about a broadcast model, and this API was basically designed for small sort of group calls. And out in the wild, when topologies change, you could be in a small call and 1,000 people or 2,000 or 5,000 people are watching it, or 1 million people are watching it, right? And then your participants array has got like 1 million entries or whatever, right? So it's what you anticipate is often is not what breaks at scale, right? And it's always useful to try and make sure you don't paint yourself into a corner from the design phase. But the eventual reality is you will be painted into a corner, but very likely for all of the reasons you did not anticipate up front. And the other thing I wanted to point out is, things really do become counterintuitive at scale. Monolithic software is sometimes good at scale. Something should fit in memory is better than putting it in disk. I forget the actual name of the speaker, but I saw a pretty interesting talk where he was an engineer from Google who worked on the original search index, who was talking about how at some point it was more efficient to store the entire search index in memory than on disk. And that inflection point only happens at a particular scale, right? So things are quite counterintuitive at scale. And an example of this is another incident we ran into. WebRTC is essentially designed as a peer-to-peer sort of communication application, right? So you create a peer connection, which is just a connection to another peer. And these are pretty heavy-duty peer connections where you have an encoder and decoder and all of these resources tied into it, right? It's designed to do one-to-one calls. And we had always assumed, quite rationally, there's some sort of threshold in how many of these peer connections you can sort of emanate out of a browser endpoint, right? And we designed all of our systems around it. And the blue line is actually media streams which go client-server, meaning which are mediated by a MCU or an SFU. And the red line is basically calls which are pure peer-to-peer. And what you see here is the number of subscribers in both peer-to-peer as well as routed calls. And we notice in production, at scale, there were people who were streaming 200 individual peer connections from a single browser endpoint, right? This is literally like 200 peer connections from a single endpoint, right? And this completely blew our mind in terms of, okay, this is completely counterintuitive. We didn't even think it was possible, but it happens in production. And we even looked at the bit rates. It's extremely good quality, right? The person who's streaming it probably has like a big fat uber powerful machine, but still it's possible and people are doing it. So I think it's useful not to over-engineer because a lot of fundamental assumptions sort of radically get changed at scale. Moving on to this is one of my favorite sort of lessons we went through, is that generalization is the enemy of performance. And all engineers, and I think this is due to our training, we are all taught to admire abstraction and generalization. If you actually think about it, all of computing is built on abstraction, and abstractions are good. But at scale, abstractions are bad. And this is a controversial point. I've had a lot of arguments with a whole bunch of people who don't agree with me, but I actually think at scale, it is better to have extremely sort of structured and optimized code than general purpose code. And the reason is there's a fine balance between the original use case which the designer of a particular library had envisioned versus what your own operational reality might be, right? And one of my favorite arguments, which I've had with tons of people, is in WebRTC, there is no real signaling mechanism, right? The standard doesn't specify how you take the SDP and give it to another endpoint in order to negotiate that connection. And as you could write a whole bunch of, you could use XMPP, you could use your own custom format to do this, you could use SIP on WebSockets, you could use any number of protocols, right? And the engineers also have this, or at least not invented here has become a bad word in that, everybody says, we need to make sure we don't have a not invented here syndrome and, sort of look at commercial alternatives or open source alternatives. But it's not really about protocols. It's about implementations. The XMPP protocol implementation, the server implementation, might have been designed with a series of design assumptions, which might not translate to what your operational workload requirements are. And so I think it's really important to not be afraid. I wouldn't say, do this all the time, but to not be afraid of stepping back and saying, maybe I have to rewrite my own memory allocator. Maybe I have to rewrite my own server, whatever that might be. Don't be afraid to do real engineering is sort of the lesson. Lesson number 4 is loose coupling, right? Loose couple only if you code for it. And this is sort of very related to the earlier point, is that loose coupling is, again, one of the core concepts in distributed systems, right? You want to loosely couple so that you can achieve a certain degree of asynchronous sort of communication. You can do retries. They are more reliable. They're more fault tolerant. But loose coupling is a little bit like multi-threaded programming, right? Things can become exponentially worse if you do not code for it. Or badly written or badly structured distributed systems are worse than monolithic software in several cases. And I think it's really important to keep that in mind as one goes through sort of thinking about loose coupling, because the first natural instinct is to come up with a loosely coupled, highly distributed sort of infrastructure, right? Lesson number 5, latency is public enemy number 1. And especially in real-time communication systems, latency is a bigger issue than fault tolerance. And let me elaborate a little bit on that. I think the standard operational model, and hopefully it's the case, it's true for most people here, is you are okay with your call dropping. Let's say I made a cell phone call to somebody, my call got dropped, that's okay, I will retry. But let's say the call has extremely choppy video, choppy audio, you have words snipped out, and you have these crackling noises. Bad quality and bad degradation in terms of in real-time communication apps are completely not optimal. And so it's really important to focus on latency and latency-related optimization before one gets to fault tolerance. And there are 2 real ways of solving this. Operationally, you need to make sure you pick the right vendors to be able to do this. And you always assume that they will screw it up. And then you design algorithmically in terms of how you can solve those problems. Mobility is a huge issue in real-time communication apps. I have a mobile app. I'm in a bad Wi-Fi network in some crazy coffee shop. How do I degrade? How do I sort of fall back effectively from the best possible experience all the way to something which is usable in some sort of an elegant path? There are other technologies like simulcast or some sort of temporal scaling, which enables you to make sure that you can provide the best possible quality to a whole bunch of people. And a quick example of that is we had these data centers set up all over the world. And if you look at the white arrow, it's basically a whole bunch of East Asian traffic, which were all going to our Hong Kong data center, right? Obviously, that's the closest point to where all of these end users reside. And what these colors show you is how bad the call was. Red is absolutely horrendous calls, right? Call experience or latency. And it's fairly obvious that we should have data centers closest to where you are operationally located. But when we actually switched out all of that traffic to Oakland, it became like 3 times better, right? So the Philippines to Hong Kong was 3 times worse than Philippines to Oakland and back, right? And I think it's really important to make sure latency optimization is sort of well understood in this process. Lesson 6 is data is your friend. And it's sort of cliched, and everybody talks about instrumentation and big data and all of that. But here's an example of, we power, for those of you who don't know, we power this real-time sort of communication app in Mozilla called Firefox Hello, which exists on every single Mozilla browser. And this graph is actually a testament to the Mozilla guys and what a wonderful job they've done in building that app. When you first looked at all of the connectivity numbers from that app, 10% of calls were failing. And we were like, oh my God, that's horrible. That's like 1 in 10 calls failing. And then when we analyzed this with very granular data, we actually found out that all of the get user media failures were basically because people got prompted and allowed deny permissions dialog. And all of them clicked deny, or at least 10% of people clicked deny, right? And that is exactly the experience you want, in that you want to pop the permissions dialog, and if people are not comfortable doing it, they should click deny. It's great, and that's the right experience. But if you didn't instrument it with the right level of granularity, you would actually think 10% of your calls fail. So I think it's really important to sort of granularly define all of this. And here's a similar graph for packet loss. The green dots are basically estimated bandwidth from the client device relative to your packet loss on iOS, and the orange ones are from Android. And just, you can see those constant lines in Android basically means bandwidth estimation is completely broken, right? Regardless of your packet loss, it always estimates the same bandwidth. We reported this to Google. Google fixed it. Again, the point I'm trying to make here is it's really important to not only instrument data, but also instrument it at the right level of granularity, right? Bad data is worse than no data, but granularity is really important. We're sort of running out of time, so I'm going to sort of skip through this really fast. Is your system is only as strong as its weakest link. And again, this is muscle memory of engineers, right? The standard operational model is, I'm going to have a tier of API servers, I'm going to have a tier of maybe call control servers, I'm going to have a tier of media servers. They all have very different scaling characteristics. Therefore, I will scale them differently. This is my most efficient deployment topology. The problem is, if you have that sort of a tier topology, yes, it's extremely efficient from a resource utilization point of view, but might not be the best, most optimal topology. Maybe if you had 2 API servers to every 10 signaling servers to 25 media servers, 1 API server being down maybe potentially takes you, if you didn't have full failover, maybe takes out 50% of traffic, even though you have like 36 servers up and running. So I think the key insight to keep in mind is that there are different availability characteristics for the sort of resource utilization topology you pick in your infrastructure. And finally, I can't stress enough, is you want to eliminate humans from the loop as much as possible. And this is because, I often have this argument. I have to give you guys this spiel. I have this argument with a whole bunch of people. And every third person comes and tells me about continuous deployment and how awesome it is to continuously deploy every 3 seconds or 5 minutes or whatever. And I think continuous deployment in real-time communication apps is a myth thus far, because technology has not fully evolved. The problem is you have these persistent connections to servers, which you can either let them drain over a period of time, or you can boot people off a call, right? But there is no way to continuously deploy to a system which has persistent connections, which doesn't have efficient renegotiation of those connections, right? And the implication of all of that is deployments to real-time communication apps are extremely expensive and have a cost associated with it. And you want to make sure that you finally balance the ability to deploy and push out new features and all of the good stuff with the operational cost and the user impact of deployment. And so we went through the natural iteration. We went through rsync, we went through Fabric scripts. We then wrote our own bash scripts because the Fabric scripts were too hard to maintain. Then we used Chef. Then we built our own system called Honeycomb, which sort of looks like that. And it's a one-stop shop operational deployment tool. And it completely, we can provision machines, and it's sort of single-click deployment, right? And so it really sort of tries and eliminates all the humans from the loop in terms of, reducing the cost, the operational cost of deployment. And so that is sort of the summary. And I think there are a whole bunch of very interesting observations we went through this process. And I could keep talking about this for another 2 hours. I know I have a big deck with 25, 30 lessons which we have learned through the process. So I'm happy to sort of take questions or talk to you guys offline and give you my thoughts, or at least explain to you guys our journey through the process. So in summary, what I'll say is, you either have to be fearless and reckless, or you have to be a little bit naive, ideally a little bit of both, for you to be able to build and operate real-time communications at scale, and it's a lot of fun. It's a really interesting problem. So thank you very much. Again, I really appreciate all of you guys being here, and happy to answer questions. Yes. Oh, excellent question. Excellent question. Absolutely. And I think the question was there a bunch of challenges with respect to browser implementations? And the answer is absolutely yes. And the reason is WebRTC is still sort of pretty evolutionary. It's sort of an evolving standard, and there's a lot of churn in the code base. And so to some degree, we are a solutions provider. So some of the value add we provide to developers is the ability to abstract all of that interoperability issues and have the developers not worry about it. So absolutely, yes, that's something we frequently sort of pay attention to. And if you were an application developer who was building an app yourself, absolutely something you want to be very wary of. And the thing I would add to that is not only browser implementations. Some of those implementations get ported to mobile devices, and which have their own little quirks, right? So it's a whole bunch of endpoint behavior which needs to be tracked carefully. Any other questions?
Do you use WebSockets behind the scenes at all?
Yes. So for all of the signaling stuff, which I think, okay, I'm not going to go back, but we do a whole bunch of signaling where you go and you need to translate you need to sort of transport the SDP to the other end, and then you want to negotiate these calls. We actually use WebSockets for that, and we also use WebSockets for a whole bunch of app level signaling and communication.
Anything around like scalability? Any issues that you faced around scalability? Because we are also using WebSockets for
Got it.
real-time communication kind of stuff, and trying to figure out the scalability aspects.
Got it. So the question was, any scalability issues around WebSockets? And I would say for the most part, no. I mean, WebSockets are pretty scalable. I think the only thing to keep in mind would be the actual SSL termination if you're using secure WebSockets, right? But I think WebSockets are pretty cool. Any other questions?
Sorry, this is not about real-time communication
Mm-hmm.
specifically, but you were talking about having private groups, making them with, randomly generated links.
Correct.
Have you had problems with brute force, people trying to crack those URLs for privacy?
That's a good question. I mean, we have not as yet. I mean, you always trade off the vanity URLs with respect to how strong you want the GUID generation or the random generation is. And so we have not had a whole bunch of issues with respect to people sort of gate crashing, randomly generated URLs, right? Not as yet. Hopefully, if it becomes even more popular, we'll have those issues. So. Any final questions? We're perfectly on time. Thank you all for sort of joining. Thanks.